do it. This might be our last unit. It depends on how much you guys are enjoying it, okay? We could cut it short and move on to something else, but if we're enjoying it, I say we stay in it because it's a good one. I think it's interesting. I think it's cool. It's got a lot of connections in it, which is why I like it. All right, so check this out. This is our kickoff. We ready? Why are you guys so giggly today? Okay, we ready? Okay. I'm waiting for everybody to stop talking. First of all, I'm recording. Thank you. All right. Here we go. Okay, pretty cool. Let me pause this for 1 second. Okay, so what questions do you have? What observations do you have? I heard it from a bunch of people. What was it? It was a Ferris wheel, right? Jonathan? The time it took to get around the Ferris wheel, right? What else? You could see the city. It was pretty. The time lapse. Good. What mathematical connections can you make to the Ferris wheel? It's circular. Okay. It's 360 degrees. Fantastic. Hold on. We got to talk one at a time so like everybody can hear it. You think it's 6 degrees per second? Yeah. Okay, that's an observation. Absolutely. Yes. Is that it? Not on kickoff, right? No phones on kickoff. Okay. Maybe if you have a picture, you'll be able to come up with more questions. There's triangles? There's triangles. There are triangles. What's the distance in between the cars? Okay, so maybe the radius, right? What else is? I heard angle of rotation. All of these things that you guys are talking about are going to matter. Okay, circumference, radius. I heard radius, diameter. What does the diameter stand for? How about, you guys are trying to give me definitions, and I just want to know what it means. It's not how long, but how. We're talking about a Ferris wheel. Would you say how long it is? How tall it is. How high are you up in the air? That's what I would want to know. How high was that Ferris wheel? That's super important, right? How high it is? Okay. So all of those things we're going to be talking about today. I don't know why I'm holding two pens. Okay. All right, so I'm going to start it, and then I'm going to give you your worksheet so you can have it for your notes. Okay, but it's not going to be something that is going to that you would see on an assessment of practice. Okay, so it's basically for you. All right, create a sketch to model the height of a rider above ground with respect to the number of revolutions on a Ferris wheel with a diameter of 40 feet. So this Ferris wheel is 40 feet tall. Okay. All right, so we're going to talk about the rotations. We're going to get on the Ferris wheel, at the bottom of the Ferris wheel. I'm saying the bottom of the Ferris wheel is at 0 right now, but I'm going to say that we are going to get on the Ferris wheel right there, and we are at 0. And we're going to talk about the number of revolutions, or the number of rotations. Okay, we call it revolution, because we're going around in a circle. Okay. So if I go all the way around the circle, where am I going to end up? Back at 0. So one revolution, each time, I'm going to come back to 0. Correct? So when I go halfway around, how high am I going to be in the air? 40. Oh, I heard pi earlier from Matthew as well. Pi is going to come into play. Okay. So each time I go halfway around, I'm going to be up here. If you go half of half, or a quarter way around the Ferris wheel, I'm going to go 20. And then 3/4, 20 again. What do you think this is going to look like? Right? So this is what it's going to look like. So super cool. We're going in a circle. We're going to talk about it. We're going in a circle, yet it's making a squiggly line, for lack of a better term right now, right? But okay. So when we're at 0, revolutions, we were at 0. At a quarter, we were 20. At a half, we were 40. At 3/4, we were 20 again. So it's completely symmetrical, right? Okay, so shape is symmetrical. Let me pause, and I'm going to go ahead and get you guys this worksheet. All right. Did anybody want to write that down? Or we're good? Okay, I'll pause it again. All right, so let's continue. Now let's talk about an underground Ferris wheel. Wouldn't that be cool? All right, so now I'm going to do an underground Ferris wheel. So this time the Ferris wheel is not going to go up 40 feet, right? It's only going to go up 20 feet, but it's also going to go down 20 feet as well. So if I'm going to get on the Ferris wheel at ground level, right here. That's where I'm getting on my Ferris wheel. So I'm technically at 0 feet. Halfway around, I'm also going to be at 0 feet, right? And so on and so forth. And then when I go a quarter of the way around, I'm going to be at 20 feet. And then 3/4 of the way around, I'm going to be at 20 feet. So it's going to do something like that. So at 0 revolutions, we were at 0, then 20, then 0, then -20, then 0. So I'll let you guys finish that up real quick. Pausing. All right. So now let me do the same thing I did last time, but let's do it with degrees. Okay, there are 360 degrees in a circle, correct? So if I start here on my Ferris wheel, I'm at 0. Notice that my circle is the same height as my graph. Okay, so check out what happens. So I'm going to be at 0 again once I go 360 degrees around, and then 720, and then 1080. Let's go, what? That's what we're going to talk about right now. So we're going to go to 180 degrees, and I'm going to be at 0 as well. Next, I'm going to talk about 90. At 90 degrees would be right here. I'm going to be up here. Do you see how that lines up? See that? 90 degrees is right here. Makes a right angle. Right? 90 degrees makes a right angle. So that's 90 degrees right there. And then this one's going to be 270. So this is 90, this is 180, this is 270, and this is 0. So when I'm at 270, that would be right here. Then I'm going to take my handy little protractor here, and I'm going to make sure that I want to know what 45 degrees would look like. So I'm going to go to 45, which, you're right, it's half of 90, but I want to see what it looks like on the circle. Okay? It's going to be half as tall, correct? It's going to be half as tall, so it's right here. There's 45. At 45 degrees, 45 is going to be in between 90, so it's going to be right about here, and I'll be this high. Then at 30 degrees, 30 degrees is right here, 60 degrees is right here. So this is going to be 30 degrees because 30, 60, 90. 30, I'm going to be this high. 60, I'm going to be this high. You don't need to, you can just eye it. I'm trying to make a point here, okay? Okay, you should start thinking about there's some connections here. All right, I want to show you what this looks like if we were to do this in slow motion. So if I were to do this, you see how it lines up? That's a 45. There's 30, 45, 60, 90. See how they're lining up like that? See how it's making that arc? So check this out. You guys are going to love this.
We have all seen pure tones illustrated as sine waves, but each moment in the sine wave formation has a different phase associated with it, from 0 degrees to 359 degrees. You can see the sine wave formation.
How cool is that?
The protractor on the left shows you the equivalent phase.
Circles are waves. Yes. Circles are waves.
If you use the various points on the rotation of the protractor and draw those points on the graph on the right, you can create a drawing of a sine wave.
Super cool, right?
If you write anything on your computer, you need to get Grammarly.
I write pretty much all day, every day.
Okay, let's close that. Alright, did anybody notice something in that video besides, let's talk about what was in the video. That wave is right here, right? As you're going, it's so super cool, as you're going around in a circle, you're creating a wave. But there was something else in that video. Did anybody catch it? It does stop at the top. You're right. There was something else in that video. Why do you think I'm using that right there? It is the same thing, but I have certain measures right there. What? They do. There is a specific reason why I have those up there, those numbers right there. Jonathan.
Oh, it's by 15.
No,
It's by 15.
this isn't by 15. That's by 30. Yes. Ireland. What? The wave does have those. What's so special about those angles? Matthew, I'm giving you a hint. What's so special about those angles? Geometry. Think back to geometry. They are cute, except for the 90. Let's see if you guys can catch it in the video again. Okay, let's watch the video again, because I want you guys to really think about this. Yeah, I don't want to spoil it.
Did it have to do with the red line?
We have all seen pure tones illustrated as sine waves, but each moment in the sine wave formation has a different phase associated with it, from 0 degrees to 359 degrees. You can see the sine wave forming here, and the round protractor on the left shows you the equivalent phase at particular moments in time. If you use the various points on the rotation of the protractor and draw those points on the graph on the right, you can create a drawing of a sine wave.
Lee? It exactly has to do something with the triangles. Oh, that's so super cool. It has everything to do with the triangles. 30, 60, and 45, a 30, 60, 90 triangle and a 45, 45 are special triangles. Yes, we are. Okay, so let's not freak out. So we are getting into trigonometric functions. With application, you guys. Hold on. So that's what's so cool about it. So in geometry we use trig, right? Guys. But now it'll have more meaning, okay? And this is a trigonometric function. This is what they look like. Those triangles, right, inside of a unit circle create, this is a sine wave. All right? Okay, so let's get past some vocabulary. That's all I want to do today is get the vocabulary going. I think I've hooked you a little bit, right? It's going to be cool. All right, it is. It's cool. All right, so on the very back of your worksheet, it asks, see, I'm not really concerned about the number 9 and number 10. It's number 11. So I want to know what a period is, what an amplitude is, and what a midline is. And I think it's more important that you come up with these definitions. So talk in your table groups about what you think an amplitude, a midline, and period is. Just take your best shot. Recorded. Okay, so what do you guys think? Let's start with whatever you guys want to start with. Raise your hand. Let's do midline. Okay. Who wants to tell me what their definition of the midline would be? Let's hear Christian. What do we want to call that? We're not going to call it the x-axis, even though it could be right now, because what do our functions do? What do all of our functions have done so far? They have transformations, right? So the middle is not always going to be on the x-axis. It can shift up and down, right? It can shift left and right, right? It can stretch. Okay, so we want to call that maybe the middle horizontal line. I have formal definitions on the next page. I just want you guys to make sense of it. You should be coming up with your own vocabulary, right, to explain things. Then you know it better. All right, what about the amplitude? The height. Ooh, I like that. The range. You know why I like that word? The range. I like the range because amplitude is not how far it goes. Right? Here we go. That is the amplitude. It's like the max height, but it goes in the negative direction too. So it's almost like absolute value, right? It's the highest it's going to go. The highest and the lowest that it's going to go. Somebody said it's a hill and a hole in last period. I thought that was a really interesting way of looking at it as well. What about a period? Dave? The points where they meet at the midline. Almost. Let's hear it, Grant. One full cycle, right? So this is not going all the way around the Ferris wheel, right? That's just going up. That's halfway through the Ferris wheel. This is 180, and this is 360. So you're right. So we would say a full cycle. All right, I've got 7 minutes, and I've got to get through quite a bit of vocabulary. So if you want to write that down, I would suggest you write the other definitions, but that's completely up to you. On the papers that I gave you. Let's get through the vocabulary, and I'll make sure we come back to these screens again tomorrow before we begin, because I just want to get through the vocabulary. That way you guys get to see it before tomorrow, okay? All right. So, compare and contrast. Absolutely. If you want to take a picture, that'd be great. Good? Okay. Let's compare and contrast these. 15 seconds in your table groups. Compare and contrast. In 5, 4, 3, 2, 1. What'd you come up with? What? You know what? That may sound simplistic, but it's not. One's a square, one's a circle. They're both graphs. One's a circular graph and one's a square graph. What else? Christian? They both have an X and Y axis. Let's hear it, Ireland. They both have waves. But this one doesn't have a wave. This one has angles, right? And this one does have waves. They both have 4 quadrants. That's the biggest one right there. Notice that the coordinate plane, we've been telling you forever that this is quadrant 1, this is 2, this is 3, and this is 4. Did you ever wonder why? We go counterclockwise on our polar plane. We call the origin the pole, which kind of makes sense, right? Right? It's the middle of the circle, right? Kind of like a tether pole, right? It goes around in a circle. And your quadrants are the same. They're going to be exactly the same. Quadrant 1, quadrant 2, quadrant 3, and quadrant 4 as I go around my Ferris wheel. So that's the second pieces of paper that I gave you. Does anybody want to take a picture of this? No pictures? We're good? Oh, I have 10 minutes. Why do I think I only had 7 minutes? We have time to write this down, because I only have one more slide to show you. Okay. More vocabulary. So talk for just about 30 seconds about what you think these words could possibly mean. And okay, so what did you guys come up with? Let's start with polar axis. What do you think the polar axis is? 0, 0? Well, this is the pole, right? Pole is in the middle. So what do you think the polar axis is? It's going to be linear, right? This is your polar axis right here.
That's your initial ray, too.
It's also going to be, well, depending on where the ray starts. Does that make sense? They all kind of have something in common. The standard position is an angle that starts, hold on guys, you're going to want to know this because this is where it gets confusing. It's the vocabulary in it, okay? The standard position is an angle that begins on the polar axis. Does it make sense? So if I say that an angle is in standard position, you know that it starts here, which brings me to an initial ray. That means this is called the initial ray. Does that make sense? Like all of those things are starting right there. But then the only way that this changes a little bit, this is the terminal ray of the angle. So this is my angle. It's in standard position because it starts at the polar axis with an initial ray and a terminal ray. Does that make sense what I just said? So if I had an angle over here, let's do an angle over here. But I want to make it different. Let's do it in pink. If I had an angle over here, I would say this is the initial ray, right? This is the initial ray. It's not in standard position because it's not at the start, it's not at 0. And this is its terminal ray, initial ray, terminal ray. It's not in standard position and it does not begin on the polar axis. What? It's just an angle. Okay? Actually, there's something I need to look up. I'm guessing, now that I said that, I'm guessing that this whole thing is the polar axis. I could be wrong. I'm going to look that up. Because when I'm speaking of that, I would say that that does start on the this angle does start on the polar axis. It's just not in standard position. Does that make sense? When we talk about angles, for the rest of this entire unit, we're going to be talking about angles that come off of here. Do you know what I'm saying? We're going to be reading all of our angles from this polar axis. Okay? This one starts from the polar axis, right? It's not in standard position, though. We would actually call this is a negative angle, because it's going in the opposite direction. Okay, I think that's enough for today. Jonathan, you have questions? Yes. Okay. Good job.